Okay, so what do you look at here for our next problem? We previously showed that this was conservative, which meant that the partial of the p, which this is our p function, we're calling it the I component part of the vector function, but the partial of it with respect to y equals the partial of q, so this is our q right here. The partial of it with respect to x, those two are equal, and so it's conservative. We showed that previously. It's not difficult to show that, but that means it's conservative. Now, if it's conservative, that means then that this vector function has a what's known as a potential function. So let's go ahead and find the potential function, little f we call it. Next here is our next problem. Okay, and so we did that for one other problem before. I think we did maybe a couple, but anyway, how do we do that? Well, we set the partial of f with respect to x. That's our partial of f, the potential function we're trying to find. Set it with respect to x equal to p. And we also set then the partial of f with respect to y equal to q. And so in this case, that would mean the partial of f with respect to x equals this 2x e to the x y plus x squared y e to the xy. And then we'll have the partial of f with respect to y equal to x cubed e to the xy plus 2y. Okay. So we know that that's the relationship that we need these things to have. All right, well, what we then do is we want to integrate one or the other. It doesn't matter which one. We can pick and choose which one. But we want to integrate, of course, this one, since this one's partial with respect to x, we'd integrate this one with respect to x. And if we look at integrating this with respect to x, well, it's going to be a little difficult, right? Because integrating that part with respect to x, looks like it's going to be parts. Same thing here. I think that would be parts. So we could do it, but it's going to be integrating with respect, integrating by parts. Now, over here, since this one's integrating with respect to y, partial with respect to y, we'd integrate. If we integrate with respect to y, that gives us f on this one. And integrating this with respect to y is a whole lot easier, because it's really just substitution on that to get that one, and that one's just the power rule. So we're going to do this one. The first one, we're going to do this one with respect to y. So we integrate both sides with respect to y. So, of course, we integrate this with respect to y. That just gives us f, which they usually write on these f of xy. Then would equal the integral of x cubed e to the xy plus 2y with respect to y. All right. So like I said, just a little u substitution for that. U equals xy. And so du, that would be x dy. So, yep, we've got the x squared. So basically it'll cancel one of those out, right? So we get x squared e to the u, so that would be xy See what I'm doing there? And like I said, this then is just power rule, so that's y squared divided by 2, so the 2's cancel, so we just have y squared there, right? Well, then this is an indefinite integral, and so we've got a constant now. In this case, since this function we're talking about is we're dealing with in terms of x and y, the constant here is not necessarily a constant. It's what we can say, though, is it's a function of x. I believe here. Yeah. We can't say that it's necessarily a constant. Now, sometimes it might work out to be a constant, but it may be something other also in terms of x. Yeah, it could be like x squared plus a constant or something like that. Okay. Well, here's the way then we can come up with how these two relate. Okay. What we're going to have to do then is we know something now, since that's our function, we know that also the partial with respect to x has to equal this. So let's take the partial here with respect to x. Which we can say it's that, or say it's that. But now we know that it's tied in with this too. So if we take the partial with respect to x of this, which is going to have to be a product rule for this one, of course that's 0. All right, so let's see, x squared times the derivative of that would be e to the xy, and then the derivative of the top, the power would be just y, right? Derivative of that 0, and then now since we're doing the derivative with respect to x, we'd have to say that's h prime, right? We don't know what it is, but we can just call it h prime. Okay, so now we know that these two. Question. Oh, I forgot the other part. Didn't I? So that would be e to the xy times the derivative of x squared, so it's 2x. Plus h prime of x, yeah. This part's 0. Okay. Yeah, that's much better because now we know that this then has to equal this, doesn't it? So 2x e to the xy plus x squared y e to the xy must equal x squared e to the xy times y plus e to the xy times 2x plus h prime of x. Okay. So for those two to be equal, yeah, h prime of x has to be 0. Because we've got everything already, right? Well, if h prime of x equals 0, how can we get back? Because we need to know, basically, we've got f of xy equals this. So we need h of x. So how do I get h of x out of this? Well, if h prime of x equals 0, h of x has to be a constant. That's right. So just leave it at c. So f of xy must equal x squared. Let's put it in a little better order. X squared, oh no, it's all right. E to the xy plus y squared plus, we found that h of x is just a constant. Like we said, it could be something involving x or it could be just a constant. And in this case, it is just a constant. There you go. So that vector function, being conservative and all, it does have a potential function, and we found out its potential function is what we see right there. Yes. Yeah. Uh-huh. Exactly. All right. So let's see if we do another one here. Find a potential function f for the conservative vector field two x y cubed z to the fourth, that's the I component, plus 3 x squared y squared z to the fourth, j component, plus 4x squared y cubed z cubed. Okay. Okay. Now, one big note for this. I did say this is a conservative vector field, and we haven't proved that this is a conservative vector field because we haven't talked about how we know if a three-dimensional vector field is conservative. There's several parts you have to show. You know, the partial with respect to x of this is equal to the partial with respect to y of that. It's later in a later section, which I'm not sure we're going to get to, but anyway, that's how you do it. It's just, you know, in 2 dimensions, you just have one partial derivative equals another partial derivative. If that's true, you got it. There's 3 that have to be the case for a 3-dimensional. All right. But we're told that this is a conservative one, so we don't have to prove it. But I'm just letting you know that if you do, it's just showing partial derivatives are equal certain ones. But since we know it's conservative, we know there's a potential function for it, and so what we do is basically you set the I component part, that's going to be your partial with respect to x. So our potential function, little f, the partial with respect to x equals the I component, 2x y cubed z to the fourth. The partial of f with respect to y equals the j component, 3x squared y squared z to the fourth. And then the partial of our potential function with respect to z equals the 4x squared y cubed z cubed. Okay. All right. So now what we can do is same as we did previously. We can integrate any one of those we want to. Maybe one's easier than another. Does it look like any of them look any easier? I mean, we're integrating this with respect to x. We integrate that with respect to y. We integrate that with respect to z. They're all just going to be power rules. Yeah. So let's integrate this with respect to x. So that'll give us f, and we're doing 3 dimensions, so 3 variable fx, y, z. That would be equal to my integral of 2xy cubed z to the fourth with respect to x. So that'll be x squared y cubed z to the fourth, as we're integrating with respect to x, plus something constant, but in this case, the y and the z are kind of our constants, right? Also. So yeah, this is a function. Since we're calling that one f, let's call this one g. Yeah, it could be some function of g with respect to y and z. So it could be a y cubed plus z cubed, or, you know, plus a constant. We just don't know. That's all we can say right now. It's something in terms of y and z. All right? Now, what we can do, though, is we can utilize the other 2 facts, and let's utilize this one. This one says that the partial of f with respect to y has to equal 3x squared y squared z to the fourth. So if I take the partial of this with respect to y, what do I get? It'd be 3x squared y squared z to the fourth. Just doing the derivative with respect to y there. And then it'd be g with respect to y, the derivative of yz. Yeah, so it'd be another partial because it could be in terms of z too. But what do you see there? These two things right here must be equal. And so what is the partial of g with respect to y? Yeah, so that thing's 0. Which means the g function has to be a constant, right? No, since the derivative is 0. Oh, yes, I'm sorry. You are correct. It has to be some function of z. Yeah. Yes, because we are talking about 3 variables, so we still got a variable there that could be considered a constant with respect to y anyway. So yeah, it's some function of z. Okay. So here's what we can say then. We can say that if we know that gyz is h of z, we now have that f of xyz equals x squared y cubed z to the fourth plus some function of z. Well, we still haven't utilized this one, so we know that the partial of f with respect to z has to equal that. So let's see what the partial of z, partial of f with respect to z is here. That would be what? So now we're doing the z, so that would be 4 x squared y cubed z cubed plus the derivative of h of z. Well, these two things now must equal and so it looks like h prime of z. This one's a pretty nice one. H prime of z equals 0. Which now we know, then that would mean h of z is a constant, since it's a one variable function. So f of xyz is x squared y cubed z to the fourth, and we ultimately found, yeah, it's just a constant that we need for that. So that was a pretty straightforward one, but you get the idea. All right. Okay. All right, let's take a look at Green's theorem. Nice little theorem. And what it does, we've been talking a little bit about line integrals, you know. And previously we talked about double integrals. And what Green's theorem does is it sets up a relationship between line integrals and double integrals. That's what we're going to do. Okay. Now, just start with here just a definition. If we have a simple closed curve, we're going to let D, because that's what Green's theorem is based off of, a simple closed curve, call it C. And then D is going to be the region enclosed by such curve, said curve. And then there's also assigned to it a positive and negative orientation. If we're going counterclockwise, that's said to have, C is said to have a positive orientation. Okay. And thus, clockwise goes is a negative orientation. Yeah, it's you know, that's our usual. I mean, we usually measure angles that way. It may have something to do with it, you know. And so if it goes the other way, it would just be negative. Negative that. And sometimes it can get a little bit funky, I guess you might say. You know, if it kind of winds around, you can start going clockwise and counterclockwise, I guess. That one might not be too bad, but no. What they also said is the region is always on the left. D is always on the left of your curve. So if you think about walking on it, D is always on the left. If you walk along it, D is always to the left. And if you come over here, it's to the left. Okay. Yeah, because this one kind of turns around, you see, and you are kind of going clockwise, you see. So it kind of has, you know, counterclockwise, quote unquote, but D is always on the left. All right. All right, here's what Green's theorem says. Let C be positively oriented piecewise smooth simple closed curve. Okay. It's a very nice setup here. Okay. And let D be the region enclosed by C. If P and Q are continuous, first order, have continuous, first order, our usual deal, have continuous first order partial derivatives. They're also pretty nice. On D. Then, here's what Green's theorem says. The line integral over C, P dx Q dy plus Q dy, our usual line integral setup. That equals the double integral over D of the partial of Q with respect to x minus the partial of P with respect to y dA. P dx plus Q dy. So notice what you do is you take the partial of this one with respect to x, and you do minus the partial of this one with respect to y. Those are equal. A line integral equals a double integral. If I had time, I'd show you one that it does work. But and so what this means is, and it goes both ways. Sometimes a line integral, because if you have different parts of the line, quote-unquote line, you have to do an integral for each part, right? If you got a line here that goes horizontal, and then you've got one that goes vertical, and then maybe you got one that's angled, and that's the first one we're going to do. You've got to do each one of those parts. You've got to evaluate the line integral on each part. Well, it usually works out you don't have that case. You just have the double integral, so you've got to you integrate twice, I guess. And maybe you have to set up, you have to find each part too for this. But anyway, it usually it works out. Sometimes it's a lot easier to do the double integral than it is the line integral. So it's a pretty nice thing. Okay, now one other thing that I added here that may or may not have noticed is this line integral. I put a little circle on it, and so that if we have, because on a line integral you don't have to have it to be closed. I mean, it can just go from this line to that line. It doesn't have to be closed up, but if it is positively oriented, simple, and closed. Now, what does a simple add to this? Remember? Closed, of course, you know what that means. But simple just means it doesn't cross over itself. You don't have a figure 8 or anything like that. That's what simple basically means. So anyway, if you've got all those things, then you can use this notation for your line integral. And that's the only way this works anyway, okay, is if it is a simple closed curve. Well, there is one other part to it that we can include, but we'll get to that in just a second, hopefully. Okay. All right. So that's Green's theorem. So let's use Green's theorem to evaluate our line integral over c xy dx plus x squared y cubed dy, where c is the triangle with vertices 0, 0, 0, 0, 1, 0, and 1, 2. And we'll use the positive orientation for that. Would just be negative if we went the other way. All right. So yeah, we've got a triangle from 0, 0 to 1, 0, then from 1, 0 to 1, 2, and then from 1, 2 to 0, 0. So that's our curve. And so positive orientation would be counterclockwise, so it would be something like that. So that's our curve C, and so D is, of course, we get to it, the inside of that. All right, now, so we want the line integral xy dx plus x squared y cubed dy. By Green's theorem, yeah, we've got positive orientation, we've got simple, we've got closed. So we can do this as a double integral instead. So the double integral would be over, like we said, that's our region D here. So we're going to do it over region D. what is it? Partial of q with respect to x minus the partial of p with respect to y dA. And so all we need to figure out here is how do we describe our region D, right? Where we can do it as a line integral. Now, and it's set up this way because dA we can define in polar as well as just normal dx dy or dy dx. But we could also use dA. We could use polar. So we have options here. In this case, I think just rectangular coordinates make sense. So how would we describe this region? Well, if we do the x's go from 0 to 1, then how would we describe the y's? Y would go from 0 up to that, right? That line there. So we need that line there. So the slope's 2. The y-intercept 0, so it's just y equals 2x, isn't it? So that's where our y's would go from 0 to 2x. We do it that way. And the x go from 0 to 1. All right, so this double integral, the way we've got it set up, we would need to do the derivative with respect to y. Well, let's get this part set up first. What would this part right here be? This is P. Remember, this is P, and this is Q. And so to go to the double integral, we want the partial of this with respect to x. So that would be 2x y cubed minus this one with respect to y, partial with respect to y. That would just be x, wouldn't it? And then, like we said, we're describing it in terms of the y first, so dy dx. So we need the limits over here. The first one, the limits of the y, so that would be 0 to 2x. And then the y's go from 0 to 1. So a little bit of adjusting there to get it set up, but payoff's pretty good because that's going to be a nice double integral. Not too difficult, right? All right, so this would be 0 to 1. We're doing integral with respect to y for this one, so that would be what? 2/4, so that would be a half xy to the fourth minus just xy, yeah. And then the y goes from 0 to 2x. So that would be integral 0 to 1, a half x times y to the fourth, so it would be what? 16x to the fourth minus x times 2x, so that would be 2x squared. So we've got 8x to the fifth here. Is that right? So that would be the integral there. Antiderivative would be 8/6, 4/3, x to the 6 minus 2/3, x to the third. Going from 0 to 1. I said that's 4/3. We wind up with 4/3 minus 2/3. 2/3. Hey, how about that? Okay. And so like we said, we could have done this without doing this. Yeah. But, doing the line integral, you have to do the you have to get the integral on this. Then you do the second part plus the integral on that. Get that line, and then the integral on that. So it had been 3 integrals we'd have to set up. And I think we'd probably be better off going this way a little. Like I said, if I had time, I would go through and show you that line integral does give you 2/3. Yeah, I mean, right. If you get, either way, it all depends on the complexity of this curve. Sure. So yeah, let's do do this one and let's see what we get. Yeah. It's crazy how that works, huh? Yeah, some are just gifted, talented, figure things out. Okay, evaluate line integral y cubed dx minus x cubed dy, where C is a circle, radius 2. Centered at the origin. Okay. So let's just get it set up here first with Green's theorem. It's the double integral over d, which d is just going to be the interior of the circle, right? I don't know if there's any reason really to draw it here because it's pretty straightforward. Just d. I know in the book sometimes they do just a half circle, so it's a little bit trickier, but yeah, the orientation we definitely yeah. To use Green's theorem, it'd be yeah. If it's negative orientation, it just makes everything negative. Yeah. Okay. The opposite. So we need the partial of q with respect to x minus the partial of p with respect to y dA, and so this case would be partial of q with respect to x. Now, be careful on this because the q here we have to include the negative, yeah, because it's in this part it's p dx plus q dx, q dy. So the q is negative x cubed. So the partial of q with respect to x would be negative 3x squared minus partial of p. P is just y cubed, so that's just 3y squared. Okay. Now, like I was saying earlier, we have our option here. We can do this double integral how we want to. Rectangular coordinates, polar coordinates. Polar is definitely a way to go with circle, isn't it? All right. And so that would mean D described in polar. Well, we got R goes from 0 to 2. Yeah. Theta is 0 to 2 pi. All right, now to describe this in polar, we know x squared plus y squared equals, factor off the negative 3 there, right? Oops, let's do it right here. And we know this is r squared, right? In polar. And the dA, now be careful, remember dA, what's the replacement for dA? It's r d r d theta. Yep. Yeah. Yeah, this was pretty nice. Doing r, yeah, it doesn't matter. We can do them separately. Well, we could do it separate. So we do r, so that would be 0 to 2, theta 0 to 2 pi. So that gives us r cubed. So we have negative 3 fourths r to the 4th. Zero to 2. Let's see, that would be negative 3/4 times 16 minus 0. So, yeah, that would be 12, negative 12. So the negative 12 theta, 0 to 2 pi, negative 24 pi. Plug in the 2 pi. All right. Double integral. Mm-hmm. According to Green's theorem, yes. I don't think it's too bad. We didn't do it. Yeah, it is. It is. Okay. Now, there is one other case we can apply Green's theorem to. You know, Green's theorem says simple closed curve. Yeah, it's not bad. Well, it turns out you can apply Green's theorem to also things with holes in them. If they're simple but have a hole. All right, so let's say C1 does this, and then C2 does that. Okay. So our C is the combination of those two, the union of those two. That's our closed curve, or our curve. Well, it turns out that the area enclosed here, D, the donut, yeah, we have drawn it. But with Green's theorem, we can actually apply it there too. Because notice this. I'm drawing these supposed to be the same. Notice here that if I cut a line right here and a line right here, then I can actually kind of make a makes the curve C, which is, you know, C. What I'm saying is C is the union of those two. Well, if you'll notice here, if I take this path here, and then I cut across here, and then up and around, and then back over here, that's a simple closed curve, right? And then if I do the same thing down here, if I go along this path, whoops, the other way though. Yes. These in here will cancel out. You got a positive and you got a negative. And so you just wind up with this curve. Well, I went the wrong way, didn't I? I did go the wrong way. Should go this way. And then this one goes this way. This one this way. All right, then the other one will go this way. So this one's going this way, but we wind up going this way. And this one comes over here. But anyway, they cancel out. And so you wind up with the same curves. So you can apply Green's theorem with things with holes in them too. All right, so let's evaluate. So we can use Green's theorem with things with holes. All right, so if we've got well, let's just do, I guess, to make it kind of quick here. Same basic line integral we had before, but where C is the boundary of the region between boundaries, I guess, of the region between x squared plus y squared equals 1 and x squared plus y squared equals 4. So C is the boundaries of those regions. with positive orientation. So, okay. So we've got a hole. And of course our region D is going to be that between. So Green's theorem does apply. So we can do this one with our same setup. Double integral over D partial of Q with respect to X minus partial of P with respect to Y dA. So Green's theorem can be applied there. So that'll work out to be double integral, what was it? Oh, negative 3x squared minus 3y squared dA. Oh, partial, sorry. Yeah. All right. Then again, we're going to use polar, and so that's just going to be negative 3r squared, again, r d theta. But notice here, the r now is not 0 to 2, it's 1 to 2. Okay. So it's the same setup, just in 0 to 2 pi. So that's all it changes. The r is 1 to 2 instead of... Okay, so what was it? Be minus 3/4 r to the 4th for the r integral. Now we're going from 1 to 2, so what does that change? 3/4 of 16 minus negative 3/4, yeah. So it'd be basically 12 plus 3/4, or negative 12 plus 3/4, which is 11 and negative 11 3/4, 11 and 1/4. Which is that 45/4? Right, because it's negative 12 plus 3/4. That's negative 11 and 1/4. Negative 45/4. Okay. Believe that? All right, that's d theta. So negative 45/4 theta from 0 is 2 pi. 0 to 2 pi. So it's negative 90 over 4 pi. Or negative 45 halves pi. All right. Something like that. That's what I got previously. So. Yeah.
Would that be doing a line integral?
Yeah. Well, yeah. The thing was you get the line integral around, but it's just two separate line integrals. Oops.
Right. Yeah, you split them up.
Yeah, you split them up, and so this one I can't remember. It goes this way, so it goes this way, and this one goes this way, and so the line integral turns out, C then is the union of all of those two, but this is D1 and D2, so you get D is these two. So you can do this line integral with this double integral over this area. Yeah, and then the this line integral is the double integral over that area, and so you just wind up with the same two things. So. I had an interesting one too I wanted to show you if I maybe have time. So that's going from the line integral to the double integral? Well, sometimes it's helpful to go from a double integral to the line integral because you can do vice versa. And it's interesting to note here how we can do that. All right, so we know that if we want to compute, say we've got, I'm trying to find the double integral over some d there, okay? Well, the area of d, do you remember how we did that? Just to find, that's computing a double integral over some function of x, and then we do that over area d. Well, if I just want to find the area of this guy, how do I do that? You just do 1 dA, right? Yeah. Okay. Well, if we're trying to find this closed area like this, we can apply Green's theorem, right? So if we set that equal to our line integral, c, p dx plus q dy, okay? Doesn't that basically say that I would need the, because this also equals, actually I want that equal to the double integral then of the partial of q with respect to x minus the partial of p with respect to y. Would that mean this must equal 1? So the area of d I can find with this double integral, okay? Now, or actually partial of q with respect to x minus the partial of p with respect to y, that must equal 1. So if I could come up with q and p functions, p and q functions that give me this, that satisfy that equation, that gives me the area of d if I do my line integral or the double integral this way. There's a couple of interesting ones. Here's some possibilities for q, p and q. We got p of xy equals 0, q of xy equals x. Yeah, partial of q with respect to x would be 1. Of course, that would be 0. 1 minus 0 gives you 1. Very simple. We could go the other way then. P of xy could be y, or negative y, and q of xy 0. Because the q of xy with respect to x, the partial of q with respect to x would be 0 still. The partial of p with respect to y would be negative 1, but we're doing the minus of it. But this one's the one I'm going to use in my next example here. P of xy equals negative 1/2 y, q of xy equals 1/2 x. Okay, so the partials are partial of that with respect to x is a half, partial of that's negative a half, but it's half minus a half, half minus a half, so that's positive 1. Well, you can use these to find the area of your region D. Okay? So what this means then is with these formulas then, the area of my region D we can find by doing this double integral instead of this one. We can do the double integral of, well, if we use this, the first example here, what do we got? Partial of q with respect to x is 0. Oh, no, is 1. 1 dx. Or dA, sorry. Which that's, wait, what am I saying? Sorry. The line integral, let's go back to this one, all right. All right, so this one is p p dx, so that's 0 dx, x dy. Okay. Then we can do the line integral. If we use this one, we would have negative y dx plus 0. Or if we use a third one, we would have the line integral negative 1/2 y dx plus 1/2 x dy. Okay. And those would all find the area of your region D. That's the enclosed region by the curve, simple closed curve C. Okay. All right, well, here's the payoff. Let me try to squeeze this one in. Here's what we can do. If we want to, we could find, we've done this, I think we did this back in Calc 1. I think it was on a quiz. Maybe not. No, I think we did the ellipsoid, but anyway. We can use this to find the area of the ellipse in general, x squared over a squared plus y squared over b squared. Well, I'm sure we can do it Calc 1 stuff, but this provides a nifty, neat little way of doing it. Okay, because what we know is that, you know, an ellipse is a simple closed curve. A, B, right? And so if we change it over to find to this line integral, so we know that the area of this thing is the line integral over this closed curve. And let's use this. I think this is the one I want to use. Yeah. We can factor off the half. So it'd be a half times okay. Now remember, the way we do those is we come up with parametric equations for this. And so, like a circle, it's kind of like a circle, but it doesn't have the same radius all the way around. You can just use A equals A cosine t, y equals B sine t. Similar with a circle, but you've got the different parameters for x and y there. But that's how you can do it for, and then t. Okay. Yeah, so substitute those in. We've got the area equals a half, then the integral 0 to 2 pi y, so we have negative y, so it'd be negative b sine t, and then dx would be negative a sine t dt. That'd be negative a sine t, and we'll put the dt at the end, plus the x would be a cosine t, dy would be just b cosine t. Oh, wait. Yeah, okay. How about that? So you get 1/2 the integral 0 to 2 pi negative ab sine squared, positive ab sine squared plus ab cosine squared. And as we know, cosine squared plus sine squared is 1, so that's just ab 0 to 2 pi. Which ab are just constants, so it'd be abt. So it'd be 1/2 ab t 0 to 2 pi 1/2 ab times 2 pi ab, AB pi. That's the area of an ellipse. Or pi AB, I think is usually right. So anyway, different things you can do with these.